Very good. Yeah, so let's go ahead and get started. So it's a great pleasure to have Dr. Kerianne Hobbs here from AFRL, although it's virtual. Still a pleasure to have you as part of the seminar series. So I'm one of the co-directors of ICON. My name is Shreyas Sundaram. I'm associate professor in electrical computer engineering. I'm together with Professor Xiaoxue Mo, who's also on the call from Aero. ICON's a relatively new center here at Purdue. It's a Center for Innovation and Control, Optimization, and Networks. We have a very large College of Engineering and a large faculty spread out across actually all the colleges here. So currently we have about 60 faculty within ICON that are tackling all aspects of autonomous systems and human autonomy interaction, AI, ML for autonomy, resilience, and security, and so forth. So it's a pleasure to have you here, and I'd like to turn it over to Neera, Dr. Neera Jain, to introduce you.
Okay, thanks, Shreyas. So again, so happy to kind of be kicking off our Human and Autonomy seminar series today with Dr. Kerianne Hobbs, who is a Safe Autonomy lead on the Autonomy Capability Team at the Air Force Research Lab, as we were talking about at Wright-Patterson Air Force Base. She works on rigorous specification analysis and bounding techniques to ensure the safety of autonomous and learning controllers for aircraft and different spacecraft applications. She's worked on the F-16 automatic collision avoidance at AFRL, as well as autonomy verification and validation research. And she finished her BS at Embry-Riddle Aeronautical University and has a master's from Air Force Institute of Technology, as well as a PhD in aerospace from Georgia Tech. So please join me in welcoming Dr. Hobbs.
Thank you so much to Neera for helping to organize this and inviting me out, and to Shreyas also for co-hosting this. This is a great opportunity to talk to an outstanding group, and I'm kind of excited. I didn't actually know about ICON, so this is a good chance for me to learn more about you guys as well. So my talk today is autonomy on a leash, and I've learned since I initially titled this that some people have a very specific definition to what leash is. But what I mean by leash is that when we have autonomous systems go out there, that there's some kind of boundary that they're allowed to operate on. They have you can almost think of it like a dog. It can go around, but it's got a leash and you can rein it back in. So that's the general idea. And so this kind of introduction to some runtime assurance approaches for complex and intelligence control systems. And a little bit more background too, just for people who aren't familiar. The Air Force Research Lab is kind of all over the country. They have different groups. Four of their main technical directorates are at Wright-Patterson Air Force Base in Dayton, Ohio. And so I'm actually under the Sensors Directorate right now, but there's several other groups as well. And the Autonomy Capability Team is a relatively new group at Sensors Directorate. They kind of started organically in 2017 with a handful of people that were participating in AI competitions. And then it's slowly grown out from there. And so now it's a larger team of people that our mission is to operationalize AI for the Air Force and Space Force. So that's kind of the group that I sit in, is looking at AI research, and I'm looking at the safety side of it. So the talk today is going to give a little bit of an introduction of what does verification and validation mean, and what are some of the considerations for autonomous systems. And then I'll talk about what is runtime assurance, and I'll give the example that was described in the abstract, which was kind of a different abstract than I normally put out there, but I think it's kind of a cool one to get people hooked and excited about technology. And then I'll talk about some of the key research areas for learning system safety, and then I'll see where I'm at on time. I want to encourage questions throughout, and kind of to spend some more time on the earlier slides. And so if we get through it really quick and nobody has any questions, we can dive into some of the examples of runtime assurance, press reinforcement learning. That's kind of the goal for today. So verification and validation. So this is really kind of asking a couple of different questions. First, how do you prove that an autonomous system is going to do what you want it to do? Or the flip side of that question is, how do you prove that an autonomous system is not going to do what you don't want it to do? So when you have a safety or a mission critical system where, if a video game is making a mistake, it may not be that big of a deal. But once you start actually putting reinforcement learning on these cyber physical systems where safety is an issue, we have to think about what are the things we want to make sure for sure that we protect against in that process. So these kind of translate to the ideas of verification and validation. There's kind of a lot of different terms out there that people might associate with this. But when we say verification, a lot of times it has to do with, did we build the system right? Does it meet some kind of specifications or requirements? And interestingly enough, that's not always the same as what we would say would be validation, which is answering the question, did we build the right system? This is asking, do we meet the customer's needs? And in the Department of Defense, we kind of usually have these two stages of testing. The first one is the development test and operations, where we're kind of seeing, okay, we've built the system, maybe something like auto GCAS, and we're going to test it out and see if it meets requirements. And then we roughly have this other area called operational test and evaluation, where we bring the operators in, we test it in different operational conditions and see, does it still make sense for meeting the customer's needs. And then a lot of this intersects really at the requirements level, which is why I work in this rigorous specification area, is how do we make sure we get the requirements correct in the beginning. It has to do with a lot of interviewing the operators out there, looking at previous systems, and doing a lot of upfront analysis. Validation can also mean, does the model match reality? So you might have heard, like, did you validate your simulator or validate your equipment or something like that? So that's kind of another definition out there of that. So before you can put a new autonomous control system or optimal control system or anything on a Air Force or any DoD aircraft, you have to go through a military airworthiness certification approach. And on the military side, it's governed by Mil Handbook 516C, which is our kind of, it lists out all this check mark kind of approach. So there's about 1,000 criteria that you have to go through and see if it say, does your control system, does it impact this criteria at all? If it does, then you have to show evidence that you meet that criteria. And it's pretty extensive. On the FAA side, for the civilian aircraft, it's even more rigorous because they usually have a requirement that there's a 1 in a billion chance of something going wrong. And so I actually have the Federal Aviation Regulations here too. It's basically like, it's like a Bible paper with, it's just, you know, this little tiny font and pages and pages. So this is kind of an example of some of the evidence that you would have to generate for that. Some things, you know, some requirements you have to, it's just inspection documentation verifies it. Some things it's a demonstration, some things you inspect. Sometimes analysis or simulation is enough. Some things specifically require a hardware or software in the loop. In terms of hazard analysis, what's cited most often in the airworthiness standards for the Air Force are these failure modes and effects analysis and testing for FMEA and FMET. And then of course, you progress up to tests where you do some tests are environmental tests, so radiation, thermal temperatures, vibration, up to then going to integrate everything and go to flight test. But one of the challenges that we have is, you know, is this the right type of evidence for autonomy? And for the controls people in the group, most of the requirements that are in these criteria are based on kind of lessons learned over many years. So something broke, and so they say, okay, now we're going to make that a criteria. But it's also written based on traditional control techniques. So it's written like assuming you have a PID controller and you have gain and phase margins. And so when we're trying to look at something like a reinforcement learning controller that then is implemented as a neural network, it doesn't make any sense anymore. There's not a check. We don't have a check mark. We don't know when that's correct or not. So it's an active research area right now to figure out how are we going to decide what type of evidence we need for autonomy. So now I'm going to switch to kind of this idea of runtime assurance. And I sent out this video here, but the real world example is from the Automatic Collision Avoidance Technologies program, which I kind of hit the lottery when I first started working at AFRL and got to work on this program, where we were finishing up the testing for the automatic ground collision avoidance system and working on the automatic mid-air collision avoidance system. And so what these systems do is that they detect when a collision is going to be imminent. In the case of the ground collision avoidance system, it actually uses GPS essentially to know where you are, and it carries a digital terrain elevation database, projects, you know, the state of your aircraft ahead in time and determine if there's going to be a collision imminent. And if there is, it takes control from the pilot, kind of switches over to this other controller, does a roll to wings level 5G pull until it's clear of the terrain and then returns the control back. And the reason that this type of system became important is that over the course of like 30 years of the F-16, they had incorporated 6 different manual warning systems to let the pilots know that a collision was imminent, whether it was commanding, you know, a pull up, altitude voice that came over, or visual signals, changing the training process, And none of those had a statistically significant impact on the number of accidents that we had for ground collisions. And the main reasons that we were seeing ground collisions were that the pilots would experience something called, they'd be so fixated on a target that they were trying to hit as part of the training process or whatever, or they were saturated with the number of tasks they're trying to monitor as aircraft become more and more complex. There's a lot going on in the cockpit beyond just flying the airplane. One of the biggest causes is something called gravity-induced loss of consciousness, which is where you're pulling so many G's in the aircraft that the gravity pulls the blood essentially out of your brain and the pilot will black out. And then there's also just kind of a loss of situational awareness, or they can also become spatially disoriented, especially if they're flying at night or in clouds and they kind of lose their sense of orientation and where they're at. So I wanted to go ahead and share this, this video and kind of step through it, and I have it up in another page. So hopefully I can come over here and show this. So I may try to pause it and explain it all the first round, and then we'll watch it through the second time. So real quick, what you're seeing here is it's actually a video out of the cockpit of the F-16. This is a training flight out in Arizona. So this is a student pilot that's actually at the controls here. There's a lot of things going on this HUD. So some of these lines, just real quick, can you see my mouse if I move it around? Okay. So these lines here, you can see like the 5, and you can see the dash lines with the 5 here and 10. That's kind of your pitch ladder. So it's kind of the nose of your aircraft, for those of maybe who aren't in aerospace. So kind of the nose of the aircraft and the pitch that you've got going on. This is the 17,210 is your mean sea level altitude. So it's how high you are in feet above mean sea level. The R down here is a radar altimeter. So that's saying how high you are above the ground based on the radar that's kind of pointing down. Some of the other things you have on here, you've got this 482 is how fast you're going, and that's in knots. And then this 5.7 down here is your number of G's that you're pulling. And something else that you're going to see, I guess I'll let it progress forward a little bit. You can see the G's, watch the G's.
Field recover.
So this is kind of the flight path marker. It's showing exactly where the aircraft is headed. Right now it's headed directly towards the ground. You can see they're pulling 8.4 Gs, which is quite a bit. And so it's actually, the pilot of this aircraft right now is actually experiencing that gravity-induced loss of consciousness. And what it looks like to them is initially, their vision will actually, I've heard that it actually kind of almost turns black and white, and then it slowly comes into a pinpoint until their vision is gone, and eventually they pass out, and it happens very quickly. And you're hearing another pilot come on over the radio and say to recover, and this is his instructor. So this is student 2 in this flight, and he's saying recover, which means pull out of the dive.
Field recover. Field recover.
And so what you're kind of also hearing a pull up, and I think you probably heard the altitude command. So those are some of the manual warning systems that are still on there. But of course, if he's blacked out and passed out in the aircraft, that's not gonna help. And then one of the flight aids, part of the kind of human machine interface piece of this, is that, and this is a huge debate too of whether we should include it or not, because initially it was just used during flight tests, but they decided they did want to actually put it on the system, is with these chevrons that come in from the sides, and as they're getting closer and they touch, then it activates the system, and so you also get this fly up and a tone that tells you that the system is activated. And so at this point, when it says fly up and the chevrons are touching, the control has switched from the human pilot to the autonomous. People will debate whether it's autonomous or automatic, but it's an automatic predefined kind of maneuver where it's doing this pull up.
Cover. Sully, knock it off. Sully 1, knock it off.
Sully 2, knock it off.
doing 9G. So when the pilot recognized that that the system turned on and he was able to actually recover during the maneuver, part of the reason why it is 5Gs is that they determined and tested that it was enough that a pilot, if they were G-locked, could recover. But when he did recognize that the pull-up was happening, it's also in there that you could aid it. So the pilot could pull back even more and do the 9Gs to get out more altitude.
You get yourself back above the floor.
But you can see how he's climbing now. And it's 7,000, 9,000, 10,000. He was at 17,000 per minute.
Sully, knock it off. Sully 1, knock it off.
Sully 2, knock it off.
All right.
And when they're saying knock it off, this is kind of them saying, okay, something has happened during the flight test. And so we're going to stop. We're not going to do the training anymore. It's knock it off. We're going to just all touch base with each other, recover, probably go return to base, debrief, figure out what happened. And that's kind of that discussion there.
You climb back above 12,000. All right.
All right, so I'm going to play it from the beginning now, so you can kind of watch it without all of my overlay. But the things to watch for are you can watch especially the altitude and see how quickly that goes down. And then you can watch the G, so you can kind of see, once the G start to get up above 8 is when he starts to pass out, and then you can see that it kind of the nose goes down and it starts to decrease in altitude.
Two, recover. Two, recover. Two, recover. Two, recover. Sully, knock it off. Sully 1, knock it off.
Sully 2, knock it off.
Two, get yourself back above the floor. Sully, knock it off. Sully 1, knock it off.
Sully 2, knock it off.
All right, two, climb back above 12,000. All right,
All right. So this is an example of what we're calling our runtime assurance system. So it's something that's monitoring the state of your aircraft or your spacecraft or your other autonomous robot while it's operating and seeing if it's going to intersect any kind of unsafe region and preventing that intersection with the unsafe region before it occurs. And now in this case, it was monitoring human pilot as a complex controller. But you can imagine there's a lot of interest in this, in particular for bounding neural network controllers as in part a way to get towards certification. That maybe we can actually define some of our certification criteria on using several of these runtime assurance systems to bound behavior. But traditionally, when we're talking about runtime assurance systems, it's something like collision avoidance, where it's not something that you would want to control the aircraft the entire time. It's just there to recover from an unsafe condition. It could also be an auto land or return to base, or some other function that it takes as well. So it's not something you wanted to necessarily control the entire time. You have a more complex controller like a human pilot or some kind of autonomous agent that's doing the main mission. But we're still kind of in this period now of trying to figure out how do we go about, using something like runtime assurance as part of the certification process. And I kind of discussed this just for a quick overview again to help some of these concepts kind of sink in. In this case, we've got a safety controller, which is the auto GCAS system, and kind of as you saw in the description or saw in the video. What it does is it actually projects the maneuver out ahead. So it's going to do a roll to wings level and then a 5G pull. So it projects what that trajectory is going to look like out ahead. And then it has a 2D projection of the terrain ahead of it based on a database of the data that it carries on board for the flight, as well as GPS information and aircraft state information. And then it adds a buffer, and the buffer can be tunable depending on how much uncertainty is in the environment, as well as the level of risk or where they're flying. If it's very mountainous or pretty flat, they can change that buffer. And so if there's an intersection with the buffer and this maneuver, it takes that backup case before it's too late. So that's kind of what the AutoGCAS safety maneuver is. The complex controller could be some form of autonomy or a human pilot. So most of the time, the complex controller actually, it's the idea of a switch. So the complex controller will be output to the plant. And the plant in this case, in controlling it, right, of course, is an aircraft or a spacecraft, or a robotic arm, or your robotic car, or whatever you're trying to drive. And so the decision logic and switch is watching for these unsafe conditions where it switches from the autonomous controller to the safety controller. So this is just one example of a type of runtime assurance, and I'll kind of talk a little bit more about some of the other types as we go in. So yeah, generally this is kind of the similar idea of, it's lost right here, of, in our case, we're looking at, okay, let's bound a neural network controller that has some desired control signal that comes out, goes through the runtime assurance. The runtime assurance potentially intervenes and then has an actual control signal that goes to the environment. And then both the runtime assurance and neural network get the current state information. We're assuming some kind of continuous cyber physical system dynamics. We're also making some assumptions that the dynamics are Lipschitz. A lot of the work that we're doing right now is looking specifically at linearized dynamics, your traditional AX plus BU systems. We're trying to formally define safe sets. In this case, this is an example of a lead aircraft and a wingman that are trying to fly information. We always want to ensure that the distance between the two aircraft is greater than some amount, like 100 feet. And so you can imagine different constraints that you can write like this in a formal set-based notation. And then there's also this idea of an invariant safe set. And so in some cases, in particular, some of the spacecraft stuff that we're doing, an invariant safe set is a place where you can go and you'll be safe for all time. So in the aircraft domain, it might be a loiter circle. In the car domain, it's parking. If you go somewhere and you park and you stop and you won't crash into something. In the spacecraft domain, we've been looking at natural motion trajectories to do a parking orbit. If you're trying to do a satellite servicing mission and you need to pause what you're doing and just go to something kind of a safe parking orbit. So those are some of the concepts that I just wanted to highlight at the beginning. So a bulk of what I'll talk about towards the end, we'll be looking at runtime assurance specifically with reinforcement learning. But first, I just want to kind of give you an overview of how that fits in the context of the different approaches we're looking at for assurance. So these are kind of what I would call the key research areas for safety of learning systems. And this is my opinion and not U.S. Air Force policy. So take it for what you would like. So our team, the Safe Autonomy team, has vision to develop approaches to guarantee acceptable behavior of reinforcement learning trained aerospace control system agents. And so we're trying to answer 4 questions. The first one is, how do you train reinforcement learning controllers with safety in mind? So how do we change the reinforcement learning process so that we consider safety? Another question we're trying to ask is, how should a reinforcement learning decision be bounded? What does it mean for it to be safe? What does it mean for it to be unsafe? What does this leash look like that we want to, what's the flight envelope that we want to operate in? But it's more than just the flight envelope. Another question we have is, how do we argue safety and evaluate it specifically for certification? Because that's one of our biggest barriers to using any kind of autonomy, is that we have to get through the certification process. And it's not even just getting through the process, it's knowing that we have confidence that it's going to perform acceptably. And then finally, what methods will we use to verify neural network behavior? I'm actually going to probably end up flipping the order of these in the literature. So on the first one is kind of what methods can be used to verify neural network decided behavior. There's been a very popular benchmark out there called the ACAS-XU benchmark, which is a mid-air collision avoidance system that's designed to replace TCAS, which is the traffic collision avoidance system that's currently on commercial aircraft that gives advisories to pilots if there's going to be a collision, kind of aid air traffic control as a last, they call it last second, but compared to like the fighter world at last second, it's closer to like usually around 20 seconds, I think is where it's at, where it commands something. But in any case, the original ACAS-XU system was built using a massive lookup table for a bunch of different conditions. So the conditions were things like the velocity of some kind of lead aircraft and wingman aircraft, like they call it intruder and own ship, the angle between the heading essentially of some lead aircraft, and then the angle between yes, I guess it would be the heading of the wingman, and then the angle between two aircraft, as well as the distance between them, and then also a time to loss of vertical separation and whatever the previous advisory were all kind of input into this optimization algorithm. They came up with, I think they had like 120 million points for these 5 variables that ended up resulting in 600 million floating point numbers that were stored in this massive lookup table. And when they looked at putting that on actual UAVs, it was often too large for some of the smaller processors that they had on board. So that became this interesting challenge of, could you use a neural network? In this case, they trained it using supervised learning, where they had labeled data sets where they kind of said, here's the data going in, and we're going to give it a bunch of points and tell it yes or no, that the weights and biases as it's adapting, right? Are they good? So what they ended up doing is they created 45 different neural networks based on the previous time to loss of vertical separation and previous advisory. And then you had the relative angles of velocities and the distance between the agents as inputs to the neural networks. And they would switch between them based on what those advisories were. And so they were able to store it with 6 hidden layers and 50 neurons each, which is relatively small, which is something that's interesting with some of these controls-based neural networks, is they're relatively small compared to some of the larger image or natural language processing neural networks, or the networks that are going to be taking in images from a video game. And so this is a relatively simple multi-layer perceptron example. And the output layer is essentially either that they're clear conflict, or it gives an advisory to turn at 1.5 degrees per second left or right, which is a weak left or weak right, which is WL or WR, or strong right or strong left. And so since they put them out there, this system, ACAS-XU and vertical CAS and several other ones that are neural network compressions, have become a popular verification benchmark. So I worked with Vanderbilt, Stony Brook, and University of Nebraska to look at some of their neural network verification and so it's NNV and NNENM tools to see what it looked like in there to analyze the system. And so we were able to kind of project uncertainty of states and then look at it in a closed loop. If you had this kind of controller in a closed loop, what decisions or advisors would it make forward in time? And could we show that that we were always going to maintain safe separation defined by this near mid-air collision avoidance cylinder? And so there's a lot of work going on in this area. It's getting better. What we looked at, we were just using Dubin's aircraft. Most of the literature is just using kind of Dubin's aircraft, but there's more and more going on in here, kind of using reachability analysis of the neural networks to try to find possible intersections of unsafe states, or people who are doing falsification analysis, trying to say, can I falsify some property of a neural network? So this is one area that I'm mostly trying to leverage and work with other professors and universities to see, can we apply this to some of the problems of interest to us, and what's the promise of this. An area that I am interested in, especially because working for the government, I'm sure that you guys will see in your project, you always assume you get requirements given to you. But on the government side, a lot of times we're the ones writing the requirements, and there's this huge concern of how do we know we're getting them right? And there's many ways to go about doing that. There's different analysis techniques that we'll use. But one of the processes, especially in terms of defining what the safety boundary looks like for autonomous systems, is something called Systems Theoretic Process Analysis, or STPA. And there's another modeling analysis, Systems Theoretic Accident Models and Processes, or STAMP. And it's based on control theory and systems theory, so it appeals to me, where you're systematically going through and you're defining all of the components of your system and the interactions between them. You're defining things as controllers with a control algorithm that decides how it's going to interact with the world, and the process model, which is kind of like its estimation of its state based on all its sensor data, right? And then some kind of controlled process. And so you could look at this as a traditional controller, kind of with what's your algorithm, what's your estimation technique based on your sensor data. But you could also look at it as a human pilot or an operator on the ground, and they have some way that they're interacting with the system, and they have some understanding, and do they have enough knowledge of what's going on, enough feedback from the system to be able to appropriately interact. So what's interesting about this analysis method compared to other hazard analysis techniques is that it does allow you to incorporate humans. It also allows you to incorporate software components and see what those interactions might be with physical components, versus a lot of hazard analysis techniques that are focused more on reliability and stochastic failure rates of components that are hardware components usually. And as you guys know, humans and software don't fail stochastically. So, and we end up with these very complex interactions in these autonomous systems, because most of the autonomous systems that we're looking at are always going to have a human in the loop. Especially working with the DoD, we have no intention to create some kind of autonomous weapons. It's part of our DoD regulations that we can't, we're not going to do that. So there's always a human in the loop for all of these systems. So I've got several papers kind of looking at this, and it's really looking at, can we use this process to come up with requirements for safety by analyzing each control action and each piece of feedback that comes between different systems. And you systematically go through and say, okay, if it provides it or doesn't provide it, or if it's too early or too late or too long or too short, depending on whether you have discrete systems or continuous systems. When it provides that action to the process under some context, it can be something unsafe. So it might be something along the lines of, if the aircraft is commanding a higher altitude on your wingman aircraft when the lead is right above it, and it could result in a collision. And so it's kind of these silly things where you end up writing these requirements out and then distilling those as to how you're going to design these runtime assurance systems is the idea there. So the next area that I wanted to kind of introduce and talk about is something called assurance cases, assurance arguments. And they're these very structured arguments that kind of require a lot of formal definitions, where we are looking at, instead of doing this checkmark based approach where we've got all this predetermined set of criteria based on lessons learned and things that have failed in the past, we want to check don't fail in our system now. Can we do something more like a law argument and argue that the system is safe? And there's also methods to kind of go at it as a prosecutor. So this is a defense of my system, and there's methods to analyze it, kind of coming as a prosecutor to say, here's where the gaps are. And so you end up with this strong argument that your system is safe. Usually they're written using something like goal structured notation, which is this example here. And there's some other properties associated with it that are kind of interesting too. But I'll wait on those for now. But this is a very high level example where you have some kind of chaser spacecraft just trying to dock with a target spacecraft with some reliability. That's kind of this claim that you're making. You're assuming that your neural network control system is effective for docking, and your strategy is that you're going to show over the docking requirements that this is safe. And you continue to break that down lower and lower and define those levels until the bottom nodes are the evidence that you attach to it, whether it's the analysis that you did or any tests that you did to argue that. And this has been used in the UK Ministry of Defense for some of their systems. It's actually been used on nuclear power plants in Europe to argue them. And there's been a couple of FDA medical devices that have presented like an assurance case argument. So we're looking at, this is a very early research project. We just had another kickoff. We did a tech sprint and we just had a kickoff to look at, the tech sprint looked at the spacecraft example just to see, is this feasible to apply to this area? And now we're looking at an aircraft formation flight example with collision avoidance RTA. So this is kind of the big question that our team is most invested in, and we have lots of partners in this area. And I kind of showed the other chart, but this is how do you train AI and ML with safety in mind? Because initially the idea is, once you've completed training, you've got a static neural network, and you can then bound it with runtime assurance at operations or flight test to assure that's safe. But should the neural network know that this runtime assurance system exists, so that there's a collision avoidance system that's about to kick on at any point in time? How does that impact your performance? The deeper we dig into this, the deeper we find all these different nuances and things to try to do in the research. So it's actually a very interesting problem and question. But for those who are not familiar, this is what a traditional reinforcement learning kind of setup is. A lot of times when you see them, the neural network controller and the reinforcement learning algorithm are all one block as the agent. I like to split them out just because there's this idea that you can switch out different reinforcement learning algorithms, have kind of the similar neural network, but you could also take the reinforcement learning algorithm off once it's trained and have a static system that's not changing when you go to flight test. And that's something that's kind of important to explain, especially to the certification community who's really concerned about how do we, especially if you're gonna have to keep changing while you're flying, how are we gonna assure that? So it kind of is a baby step. Probably have things are not changing, that they're just trained during simulation and then you take it to flight test. So in this case, you've got a neural network controller that's sending that desired control signal to the environment, and then the environment's updating the state. It's also giving a reward to the reinforcement learning algorithm. And that reinforcement learning algorithm is interacting, it knows what the desired control signal is, and this is the policies. It's kind of like how it decides what to do and what steps it wants to take. It's kind of like the analogy to the control algorithm. And so it's updating the weights and biases in the neural network based on the reward that it gets. And it's doing this. There's a variety of different methods. Most of what we've been doing is using proximal policy optimization, which is a like actor critic form that's kind of like, oh, I don't want to go in super deep on that. But that's what we've been mostly looking at. There's other methods that you could use, and we're also finding that, I'll dive into that later, but other methods you can use. It also gets a state update, and then over time, it's slowly changing its behavior to learn how to operate in the environment. So an example for this might be in the spacecraft docking scenario. It's just trying a bunch of random actions, and then it's getting rewards. And there's different reasons that you could end the simulation. You could end it because it runs out of time, or it runs out of fuel, or it goes out of bounds too far away. But over many, many simulations, thousands or millions of simulations, it does enough random permutations that it eventually learns to dock. And part of that is the rewards that you give. So rewards can be sparse, which means that an example of a sparse reward would be, I'm going to give you a +1 when you're done docking, and you get it once at the end. An example of a dense reward is something that's more every time step. So every time step that you get closer to docking, you're going to get a reward. So those are kind of just different, some high level definitions of reinforcement learning for people who are unfamiliar. So what we're doing is kind of between the neural network agent piece and the environment, inserting one of these runtime assurance systems, and we're looking at different variations of giving a penalty when the switch happens. So the part of the reward system that comes back is actually including a penalty for that switching. Sometimes we look at what if it doesn't. We compare that to cases where we're training, where we just give it a penalty for things like crashing, and seeing, okay, if you're doing this with runtime assurance versus just penalizing it, what's the difference that you get in there? And one thing that's interesting about this one too is that this is an example of like auto GCAS is this way, where there isn't a defined switch, but there are other approaches that are coming out. They're more optimization based, like active set invariance filtering using control barrier functions would be kind of the papers to look up in this area. But instead of switching to a different backup controller, what these systems do is that they are trying to minimize the difference between what the neural network would command and what's safe. So they're as minimally invasive as possible, and you get as close to possible as what the neural network would have commanded you to do before before it activates. And usually it's a smaller amount. It may operate more continuously throughout with a small amount of signal or a small amount of difference versus something that is switching completely to this other controller for a short period of time to get you out of trouble and then returning the control back. So some advantages and disadvantages of the different approaches is that the switching one we found usually trains a lot faster, in part because the optimization, depending on how efficient your optimization algorithm is, you guys know that it can take a long time for it to converge, and it's probably faster in real time, but when you're trying to do reinforcement learning, you're doing millions of runs and it's optimizing every single run, every single episode that you're running. It can take, we've seen like 13, 14 times longer to do the training, to train the neural network to do a task. And then of course we have the environment where you're testing. And what's interesting here is that we are learning that sometimes maybe you want a different runtime assurance algorithm during the training process than you have during the testing process. And the reason to do that is one, for speed, that if you have a simpler runtime assurance algorithm that doesn't take as long to train, but it learns, it still is able to learn the task, and that might be better. And then you can use the optimal, very low, minimal interference one during the test. It also gives it more space to operate in. A lot of times, some of the ones that are switching sometimes can constrain your space more, depending. You could also use something that's a very clunky, simple RTA during the training process. That maybe it's doing some kind of Euler approximation of the dynamics or something to run as fast as possible. And then go to something that's more real during the dynamics. Some of our initial results have shown that the neural network controller learns to avoid activating the runtime assurance when it's a simplex-based switching one, because it takes it so far away from its original goal that it learns, hey, avoid this region where it activates. Whereas when it's a more optimal backup control situation, it actually starts to learn to depend on it for fine-tuned control as you get closer to the boundary, which in some cases could be very undesirable, because that means that you're essentially learning to go use this optimal controller and you're constantly on the verge of some kind of unsafe state. So you're increasing your risk throughout. So this is kind of a high-level overview of kind of traditional reinforcement learning with the switching version, the optimization base, and then this idea that you can have different ones that you switch out when you go to test and you're no longer training your neural network. And that's kind of another level out of a review that we talked about some of the reachability techniques that we're interested in, the system theoretic process analysis to figure out. So the reachability is looking at, can we actually analyze the neural network? System theoretic process analysis is answering the question of how do we figure out what boundaries, what things we want to protect. The assurance case generation is saying, okay, if our certification approach is based on these check marks that don't apply to neural network controllers, can we take an alternative approach and argue safety instead? And then finally, in the runtime assurance areas, how do we design these backup control systems? What are the pros and cons of different approaches? And then what do you use during training versus what do you use during flight test? And then one thing I also wanted to throw out there is that we have some aerospace safe reinforcement learning benchmarks that are out on GitHub. We're still waiting on the paper to go through public release that describes all the dynamics of it. But we do have a 2D docking example and a 3D docking example with defined safety constraints, as well as 2D Dubins and 3D Dubins that are trying to do a formation flight rejoin while having collision avoidance. The docking constraints is that you have to slow down as you come into dock as part of that. There's more pieces coming soon that these are actively being developed, and we're getting it to a point where we can put it through the Air Force public release process and then be able to post it online. So that's what's there now. If anybody wants to kind of go out and try them, if you're interested in collaborating with our group, this is a good place to start. Yeah, but our papers on this will be coming out at IEEE Aerospace in March. All right. With that, I'm happy to answer any questions. So I expect that I got too excited and talked a little bit longer to go over some of the results, but I also want to highlight that we do have internships available this summer with our group. And then you can go to afrlscholars.usra.edu to find out more, and the deadline is January 10th.
All right, thank you so much, Kerianne. That was excellent and really insightful, and a really great level also of accessibility for all of our graduate students. So thank you so much. I'm going to open it up for questions. Maybe I'll start with one from the very beginning. With when you were describing the video that you shared with us, I think you mentioned that the idea of the chevron coming together, there was some contention about whether or not to include that from an HMI, human machine interface perspective. It seemed really helpful to me in sort of seeing it, that there would be some type of visual trigger. So I was just curious if you were able to share what was the argument for not having some type of visual indicator.
Right. Well, one of the big challenges that we have is calibration of trust. And there's another person who works at AFRL, Dr. Joe Lyons, who's an expert kind of trust analysis. But one of the areas is you don't want somebody to over trust the system. And so the concern with the chevrons was that people might have overconfidence. Oh, it's about to turn on, it's about to save me, and so I can maybe take more risk than I would have otherwise, because they know the system is here to protect me. And then maybe having overconfidence in the solution was one of our concerns, is that we didn't want it to change the way that the pilots were flying. Was kind of the idea. So it was good to have in flight tests, but then the pilots wanted it there, so it became, for them to have better situational awareness of their aircraft outweighed the concerns over that it might change how they flew.
Okay, that's
Hi,
really
Kerianne. This is Oshai. Thank you very much for the talk. And I do have one question. It's very interesting that you have this switching mode between the safety and also the intelligent mode for autonomy. So, my question is for the decision logic to determine this kind of switching. What is your method to avoid like chattering?
Yeah, no, that's a huge challenge, right? And so it depends on the system. In some cases, like if you're designing a relatively simple system, maybe you have the system terminate at a point beyond when it turned on. So say, in our case, it doesn't necessarily go on distance, but say you have a collision avoidance system that goes on distance, and you'll turn on when you're going to go within 1,000 feet, and then you turn off when you're 2,000 feet. So that way the difference between the start and stop ends up, so you're not on this boundary where you're right at 1,000 feet, it's constantly turning on and off, right? And you're getting that chatter. That's one way to deal with it. Other ways to deal with it are having some of the mode logic that you include, where you have maybe some awareness of how often it turned on. That's almost looking at it from a fault standpoint. But there are a variety of different ways to kind of try to prevent the chatter, and it just depends. It's very context specific, I think.
Yes, is it possible that if safety and also the autonomy are not hard constraints, so we could formulate each of this and the objective function, then we could look at the safety and the internal objective function or autonomy, and the other one is external. Then one could actually to achieve both, that's more like a double layer optimization. Then if there is a tunable parameter, then we could develop a way to tune, the internal system also optimize the external objective function. So that's one way I could think about. I'm not sure whether, that will be solve constraints. Another way is just a simple combination of this kind of convex combination of these two objectives. What is your, your vision on this kind of, using objective functions or optimization to deal with this kind of situation?
I think it becomes, like I said, it's kind of very context dependent, because some situations the chatter is actually okay too, if it's not having a drastic impact. So I think there's also that element too of switching versus the optimization. The optimization, of course, is going to be a more smooth approach, or it's going to be a relatively small amount of impact versus the switching, which a lot of the switching ones that they've got some predefined maneuver that they have canned that they'd go to, versus an optimization technique that actually optimizes the maneuver that you're doing based on the scenario that you're in.
Thank you.
We've got a question in the chat. Actually, Jianqi, if you want to go ahead and just unmute and ask it yourself, I think that would be fine.
Hello. Hi, Professor Dr. Hobbs. I have this question. So when you're doing the training the agent, are you actually introduce the pilot's flying record to accelerate the training since the agent is the agent is also doing the like similar job as human or doing the similar decision as a human pilot. So I think that might be something useful. Could you talk about that a little bit? Thanks.
Yeah, and that's a great question. It kind of gets to this like expert systems, and a lot of the initial approaches to designing autonomy is kind of around, okay, autonomous system, the best way to go about it is to use our best experts, take the human knowledge, try to encode it into something like a neural network. And it's definitely one approach to it. And I think it depends on the scenario, but they were finding, like we took some inspiration from like the Alpha Star StarCraft training, where initially I think they did it as an expert system where they had expert StarCraft video game players and tried to encode some of the rules that they did. But after that, they ended up just training the reinforcement learning from scratch and found that just by kind of these random chance things that they did, they were able to come up with a better solution and explore a different space than they would have if they had started with that's another approach too, is to start with a neural network that's kind of trained based on expert systems kind of knowledge and then put it through reinforcement learning. But it can limit the exploration phase and kind of be more in the exploitation phase of the optimization. But I think there's still a lot more to be explored in this area. There's kind of a lot of interesting work going on too, and how can you have a human that's even providing input during the training process as extra rewards or whatever it happens to be, to maybe influence it, make it go faster.
Thank you.
Are there any other questions? We're doing on time.
Hey, Kerianne, I can ask a question. This is really fascinating stuff, and particularly the certification aspect is fascinating just because it's high stakes, right? And I was kind of interested in hearing about how the human aspect is included in the certification. Are there kind of bounded, reasonable behaviors that the certification accounts for? And if the human goes crazy, all bets are off. And second, is there a difference in designing these kinds of systems for highly specialized and compliant humans like Air Force pilots as opposed to, let's say, an autonomous vehicle where anybody can get in the car? Are there different perspectives on designing for those systems?
No, I think that's definitely the case. So there's a lot of assumptions that you make, and it's almost part of the challenge of this new paradigm is that when you have a human pilot, you're assuming that they've got the self-preservation mechanisms, they've got their years of human experience, it's common. There's more of a licensure kind of paradigm on like certifying a human pilot, that they have some training they go through, they have a test they take, and then you trust them. But yeah, when you're designing some of these systems, it's not necessarily designing for the fact that the human is intentionally doing something dangerous. So one of the things that was interesting is we actually had people like newscasters and stuff that were, newspapers that were calling us after the Germanwings incident. I don't know if you remember that, back in like 2012 or 2013 or something time frame, where the aircraft, the pilot actually flew the aircraft intentionally into the side of a mountain. And they were saying, could auto GCAS have prevented that? And I said, no, because we're not accounting for the fact that a pilot is intentionally trying to do this. That we're assuming there's some assumptions there that the pilot's not trying to do it, because there's human factors there that that we also want to protect in case there's some kind of fault in the system, right? And they have the pilot have the ability to turn the system off if they want to, and so in that case, you're not going to provide that safety. So there are definitely different considerations depending on if it's a human pilot or if it's an autonomous system. And I think that's part of why there's a lot of interest in the runtime assurance as a certification path, is that, maybe it allows us to, we have some things that we encode in the training process in terms of rewards and the rules that it has to follow and the objective function that we're trying to optimize. But the runtime assurance allows us another way to kind of explicitly state the aircraft shall never do this, it should always stay in this boundary that we've defined, and they can watch for those kind of situations. And there is a different thought process too in terms of the level of reliability that it has to have if it's an entirely unmanned system versus if it's manned. That the demand for rigor in the backup system goes up.
And just to follow up on that, with the, with these new approaches, if you consider something like the MCAS system on the Max, right, where there was this kind of weird interaction between the humans and the system essentially getting turned off every time the human interacted with it, which compounded the failures, would those kinds of kind of subtle, emergent type of behaviors be captured by some of these new certification techniques in this paradigm?
I mean, I think something like the stamp or STPA, I haven't seen it applied, so I can't say for sure, but a big portion of that is kind of looking at what type of information goes back and forth and what opportunities are there for a human to not have awareness of a situation that's demanded, or that they need for their situational awareness. There's also this general challenge of graceful degradation and how much time do you have when there's some kind of faulty system for the human pilot to react. Because one of the challenges right now is that the autonomy will keep operating until it can't anymore, and then it kind of throws up its hands and say, okay, human, take over. And what state is the human mind in? So there's a lot, I'm sure you guys are probably more well-versed than I am on some of this, that there's a lot of research still left to be done in this area too, and how that human interaction plays. Most of my research is looked at just knowing what types of interaction you would want the human to have with the system, like, especially when you're dealing with potential for faults, that there might be a chance where they want to take manual control, or they want to turn the backup controller off, or sometimes, like in the case of auto TCAS, there's a pilot activated recovery system where if the pilot has lost situational awareness and they don't know where the horizon is anymore, that they can push this button and they go to wings level. So there might be situations where you just want to manually activate that backup system. Especially if you're doing something like docking or aerial refueling, there might be a case where somebody who can see what's going on, that's watching the situation, doesn't like what they're seeing the autonomy do, and so there's a kind of a stop button where it can go to some safe invariant state and sit there. So that's kind of how I've thought about it, more in those terms. But I do work with people who do research and trust and try to incorporate, okay, what does this mean for as far as an engineering requirement for what I'm trying to do?
Thanks a lot.
Okay, we've just got a couple minutes. If there aren't any other questions, I have one maybe last one that I wanted to ask, sort of builds on some of the previous questions. But obviously machine learning, AI, techniques like reinforcement learning are being used across the board for a lot of different applications. I was curious, maybe really from your own experience and perspective, how effective do you feel that it is, right? Like, oh, you know what? Well, okay. Or more specifically, what would be? Yeah. Let me just ask that question. I think we have one more from another colleague.
I think we still have a long way to go. And a lot of people will ask me too when I present on some of this material and I go deeper in just the general technical results, or like, why are you using reinforcement learning for this when you could use a model predictive controller or something and get better results and have better verification evidence of it. And so right now, I think it's definitely still in its infancy. We've seen some interesting results, like especially in terms of the state space that it can deal with, and like AlphaGo and StarCraft, the complexity of this game that's partially observable and all of that's kind of interesting. So I don't know, I'm kind of open-minded and where maybe we could go. I think there's a lot more to explore in the area. But yeah, we're not anywhere close, I think, to hitting a wall where it's like there's not anything left. We've kind of explored it all, right? So I don't know.
Yeah, sure, absolutely.
I'm not ready to hang my hat on it and say reinforcement learning is the be all end all. Like, I'm ready to go back to the model predictive control world and do, depend on traditional control techniques when they are effective, and that works great. I think it's really going to be in these really complex scenarios where you've got, I'm thinking too, even like with all the like space traffic management issues or urban air mobility, and you're trying to route all these different aircraft and trying to do all this complex scheduling and the scale of it. Are those potential applications for it? I think there's a lot of room for creativity.
Excellent. And then Nina, do you want to go ahead and ask your question?
I just want to mention that we are working on docking underwater, and the docking part was exciting, and I would like to talk more in future or get connected, because we are doing all these problems underwater.
Well, that's great. I think one of the things that's interesting is when you bring it up a level, how similar the problems are.
Absolutely, absolutely.
The spacecraft docking, the underwater docking is also similar to like aerial refueling, where you're having an aircraft connect and get fuel. And so there's almost this interest too in how do we build in more flexibility in the agents, that you could train an agent that could do underwater docking and could do spacecraft docking and could do, so that would be really interesting as a researcher.
Fantastic. I exactly wanted to talk to you about this route of understanding the problems, across domain.
Mm-hmm.
And so before I wrap up, just for the faculty, I'll be sending out a message. Dr. Hobbs didn't have extra time in our schedule today to have one-on-one meetings with faculty, but we are going to try to schedule those next week. So I'll send out a message, and folks who are interested in having follow-up conversations with her absolutely can do so. And obviously feel free to reach out to her on your own as well. So let's thank Dr. Hobbs again for this excellent talk. And I think we're right at the end of the hour. So everyone have a great rest of your Friday and a good weekend. Thanks again, Dr. Hobbs.
Yep. Thank you. Thanks, Neera.
Thank you.
Bye.
Bye.
Bye.